In today's lecture, we are going to talk about generalizations of the second fundamental theorem of calculus for double integrals, and that is called Green's theorem. So in today's lecture, we are going to deal with something called Green's theorem. So let us recall first what exactly was the second fundamental theorem of calculus. That suppose I have a function f from closed interval a b to r. Let us also assume that f prime is continuous. Then we have proved that integral from a to b f prime x dx turns out to be fb minus fa. In all the lectures from now on, we will seek for generalizations of this when the left hand integral is generalized to a double integral or a triple integral or things like that. Today we are going to deal with double integrals. Now we already have one generalization of this for line integrals. That is, if I have a function f from R3 to R such that f is continuously differentiable, that is derivative of f is also continuous, and C is a differentiable curve, then we have proved that this is true. Let us see a differentiable curve, let us say on the interval a b, then grad f, which is a vector field, dot ds integral over c, that turns out to be f of cb minus f of ca. Okay, this is the result which we have proved. It uses the first one, that is the classical second fundamental theorem. In today's lecture, I am going to generalize further now for double integrals. Now if you look at the first one, that I have an integral over an interval that comes to fb minus fa, that is points. Now if I try with some region like this, this is a region R, its boundary is a curve C. Then if I want to generalize the first result, that is the second fundamental theorem of calculus, I should have something like double integral over R of some function which depends on a given function f. I will right now call it ff. It should be given by the line integral of a function f over c. You know, the dimension comes down to one less. In the first one, there was an interval. I looked at the end, the boundary of that interval, which comes out to be 2 points. Here I have the interval ab, this is a, this is b. Then the boundary of this interval are these 2 points a and b. Finally, the integral of the derivative of f is given in terms of the value of the function at the boundary points. If you look at the second one, what had been said is, suppose this is the curve C, this point is A and this point is B, okay, and I have integral of something, the integrand depends on the function f, then again its value is given by the value of the function at the boundary points, that is CA and CB. Okay. Now the same kind of thing I want to do now for double integrals, and that is Green's theorem. But before I start, I will need certain notations. So first I define something. Its definition of a simple closed curve, that is what we will need. So let us say C is a curve we will deal only with R2 now. I always assume C is continuously differentiable, because in most of the cases you will at least have differentiability. Continuity may not be there, but continuously differentiable is not really necessary. You can work with differentiable curves. Then C is called a closed curve if CA equal to CB. That is, if this is A and this is B, suppose C starts from here, this is CA, then CA is same as CB, that is, it is closed. Okay? That means the initial point and the final point are same, and C is called simple if there is no crossing in the curve. That is, if CT1 is not equal to CT2 for T1 not equals to T2. That is, given to different points, given to different parameters T1 and T2, CT1 is not same as CT2. That means if I look at a curve of this kind, suppose this is my curve, then this curve is not a simple curve. This is not simple. Why? Because for some value of parameter T1, suppose this is the direction of the curve, for one parameter I come to this point, then I go along this curve, then I come back and again I pass through the same point, for a different value of the parameter. That means there exists T1 and T2 such that CT1 is equals to CT2. That means this curve is not simple. So this kind of curves we are not going to deal with. So what is a simple closed curve? This is a curve for which the initial point is same as the final point. That is the first condition. Second one is the fact that curve is simple means that given to different values of parameters T1 and T2, the corresponding points on the curves CT1 and CT2, they are different, they are not same. Okay? With this now, that what we are going to deal with is certain directions, that whenever I talk about a region R, this is a region R whose boundary is a curve C. Now this curve C has a direction. I am always going to work with a direction of C in such a fashion that the region in question which I am going to deal with is always on the left hand side of the curve. That means, suppose I am standing on the curve C at this point, then I give this direction. That means I am walking along the curve on the given direction. If I do that, then you can see that the region which I am bothered about, that is R, that is actually on the left hand side of myself. Suppose the situation was different. Suppose this inside is R, and suppose I am walking in this direction. Then if I am standing on this curve at this point and walking in the given direction, then the region R is actually in the right hand side of mine, which I am not going to work with. So this is the case I am going to work with, that you choose the direction of the curve C in such a fashion that the region prescribed, that is the region bounded by the curve, is always on the left hand side of myself. Okay? With this, so when I am integrating on the curve, suppose I am talking about a line integral f dot ds. To prescribe the direction of the curve, what I do is I draw this here, then I draw an arrow. So that gives me the direction of the curve, which way it is moving. So here it means that the region R is always on the left hand side of myself. Okay? Now let us come to the statement of Green's theorem. Let C be a simple closed curve. of finite arc length. In applications, you will always see that this condition will be given to us. And let R be the region bounded by C. Consider the functions, two functions m from R2 to R. Here what I mean is Green's theorem on plane, that is C is a simple closed curve in R2. Now consider functions m from R2 to R and n from R2 to R such that m n del n del x, that is the partial derivative with respect to x, del m del y are continuous. That is, I am assuming the existence of the partial derivatives also. Then the following is true, that double integral over R del n del x minus del m del y. Look at the double integral dx dy. So this is a double integral. If I want an analog of the second fundamental theorem of calculus, now the right hand side should be an integral of one dimension less, that is, it should be a thinner one. So it should be an integral over the boundary C. Well, it is integral over C specified by this direction m dx plus n dy. By now you understand the meaning of this line integral. So this is precisely what Green's theorem says. Now we will go for the proof of this. Well, for the proof, what I do is I will assume some condition on the curve C and prove the result under those conditions, because the general theorem would be a bit difficult to prove, although I will show by some examples that the conditions which I am assuming on the curve C are not really necessary. Without those conditions also Green's theorem is true. Okay? So let us go to the proof of this. So once before, the statement is this, that you look at the double integral over R del n del x minus del m del y dx dy, that turns out to be a line integral over the boundary of the integrand is m dx plus n dy. Okay? So let us go to the proof of this. First let me draw a picture for you which would help me. Okay, let us say the simple closed curve is this. This point is A, this point is B. R is the inside region, so I choose this direction. Now from A to B, if I look at the first portion of the curve, this I am calling C1. So C1, let us say, is y equal to f1x, and the portion from B to A which goes in the reverse direction I call C2, which is, let us say, the graph of y equals to f2x. So the whole boundary C is actually C1 union C2. Now I make an assumption on the curve C which this picture actually satisfies. The condition is, I will write it here separately, that any line parallel to axis it may be x-axis, maybe y-axis, intersects C at the most at 2 points. For example, if I draw a line parallel to the y-axis, it intersects the curve twice, at this point, at this point. If I draw a curve parallel to the x-axis, it intersects the curve at 2 points. So this curve satisfies my property. But some curve which does not satisfy this, but you would like to work with perhaps, is a rectangle. Suppose I choose this rectangle. Then is the condition that any line parallel to the axis intersects this curve at the most 2 points satisfied? I say no. Because if I look at this line parallel to the y-axis, it satisfies the curve at 2 points, fine. But if I look at this line, this left-hand line, it intersects the given curve at infinitely many points. So a rectangle is not a curve which satisfies my assumption, and hence the proof which I am going to give for Green's theorem will not apply for rectangles. Okay? So we will see differently later that what exactly happens for rectangles. So let us start. What we will do is, first let us say C1, for this x varies from, and the curve is given by x, f1x. This is my C1. C2, here x varies again from B to A, actually from A to B, but the direction is different. Here the curve is x, f2x. Notice one switch I have observed while doing line integral, that you take a curve C in one direction of, let us say, of increasing parameters, and look at the line integral of the function. Now again you can look at the same curve with the decreasing value of parameters, that is changing the direction. Then how those two line integrals are connected, that we have seen. It turns out that one is negative of the other. That is, if C is the curve in one direction and minus C is the curve, same curve in the reverse direction, then integral over C f dot ds is minus integral over minus C f dot ds. Okay? This is something which we have noted. Now let us start with the calculations. So first I will see what is double integral over R del m del y dx dy. Okay? Because if you look at the double integral which I have written in Green's theorem, statement of Green's theorem, it involves two terms, del n del x minus del m del y. Now it is the portion del m del y which I am going to deal with first. You will see later that del n del x can be tackled exactly the same way as del m del y. So let me first start with del m del y. So I write it as an iterated integral. So first the variation of x, which is a to b, then corresponding variation of y, that is from f1x to f2x, and then I write del m del y dx dy. Actually, to be very precise, I should write del m del y of xy, because that is also a function of two variables, but that is what I mean when I write del m del y. Now I write this as integral a to b, I put a bracket here, I write integral f1x to f2x. So this integral is going to be an y integral only. It is del m del y dy then dx. Okay. Now I concentrate on the inner integral. I say this inner integral can be evaluated by the second fundamental theorem of calculus, because if I fix x, then as a function of y, the function m is differentiable, and what I am looking at, the integrand, is nothing but the derivative of that function, which I am integrating from the limit f1x to f2x, where x is fixed for a fixed x. So I can apply second fundamental theorem of calculus to get that this is integral a to b m of x f2x minus m of x f1x whole thing dx. Now I quickly separate the integral. It is integral a to b m x f2x minus integral a to b m x f1x dx. So I have a dx here, I should have a dx here also. Now first I concentrate on the first integral. What is this? I had a curve C1, this is my C1, this is A, this is B. I am going through the increasing value of parameters. This is C1, that is y equal to f1x. So the curve is x f1x. I am trying to look at the line integral of a function m which is real valued. So I should look at m of x f1x dot, the second coordinate of m is 0, so I will put 0 here, dot the derivative of the curve, that is derivative of x, which is 1, times f1 prime x. Okay. If I calculate, what I get is nothing but mx f1x. So once again, I have the function m. That function I am considering it as a function from R2 to R2 given by mxy, xy going to mxy comma 0. So it's a function on R2. That is what I have written here. Then I take the dot product with the derivative of the curve. The curve is x f1x. So if I look at the derivative, it turns out to be 1 comma f1 prime x. Then I look at the scalar product of the product of these two vectors. What I get then is m of x f1x. So it is very clear then, I keep the first integral as it is. This one is minus in this direction over C1 m dot ds. Now for the first integral, again notice I will be now looking at C2, which goes in the reverse direction from b to a. So write it from minus integral b to a m x f2x dx minus integral over C1, which I am not changing. I already got what I want, m dot ds. Then by the analogous fashion, if I apply the construction of line integral, then this is nothing but integral over C2 m dot ds. So the end result is minus integral over C in this direction m dot ds. Now if you calculate the other one, so what we have proved so far is that double integral over R minus del m del y dx dy, that is integral over C in this direction m dx. Now it is exactly the analogous calculation that would tell you that double integral over r del n del x dx dy, that is integral over c n dy. Okay. Adding this, I get the final result, the double integral over r del n del x minus del m del y dx dy, that is integral over c m dx plus n dy. Now this is the equality which I did not prove. I will leave it as an exercise for you. What you have to do is, you use the same technique which I applied for del m del y, but there I was looking at lines parallel to the y axis, and then I got two curves f1x and f2x. Here what you will do is, you will draw a line parallels to the x axis and look at two functions g1y and g2y and apply the second fundamental theorem, and the procedure is exactly same as the previous one. There is absolutely no complications. But I am using the fact that you take any line which is parallel to any one of the axes, then it intersects the curve at the most at 2 points, right? These lines I was using, which I have worked with. Similarly, I have to look at these lines also. So lines parallel to any of the axes intersects the curve at 2 points becomes necessary for this proof. But in general, for the statement of the theorem, it's not needed. Without this condition also, the theorem goes through. That is, if you take any simple closed curve C and R is the region bounded by that, you take the functions m and n satisfying the conditions which I said, then this relation is true. Okay, fine. Now let us see some examples of and applications of Green's theorem. Let us look at the first one. Let us look at this line integral over c y plus 3x dx plus twice y minus x dy. What is the curve C? C is this curve, 4x square plus y square equals to 4. That is, it's an ellipse. Okay. Over this curve, I am looking at the integral. So what I do is, to apply Green's theorem now, let me assume that mxy equals to y plus 3x and nxy equals to 2y minus x. Then what I will be needing to apply Green's theorem is del n del x, which is equals to minus 1, and del m del y, which is equals to 1. So the given integral, if I call it I, let me take this direction, then integral over c y plus 3x dx plus twice y minus x dy, that is equals to, then by Green's theorem, double integral over the region which is an ellipse, I call it R, then del n del x minus del m del y, which in this case is minus 2 dx dy. That is minus 2 times area bounded by an ellipse of this form. Okay. But if I look at the ellipse, x square by a square plus y square by b square equals to 1, then we know that area of that ellipse is actually pi ab. So in this case, a equals to 1, b equals to 2. So area is pi into 2. So the answer is minus 4 pi, which you can check is correct by evaluating the line integral just by hand, using the parametric representation of the ellipse at squared twice at. If you use that and evaluate this line integral, you will see that you get the correct answer. Okay, so this as an exercise I will include. Evaluate the above line integral using parametric representation of the ellipse and verify that it is minus 4 pi. Okay. Now let us go to the second example, where I will get an expression for an area of a region bounded by a curve, bounded by a simple closed curve xt yt, a lesser equals to t lesser equals to p, let us say. Okay. Now what is area? Usually it is double integral over r dx dy. Okay. So if I want to use Green's theorem, that would imply that del n del x minus del m del y must be equals to 1. Okay. Otherwise there is no chance of doing this. So I choose n xy, let us say, to be equals to half x, and m xy to be equals to minus half y. Okay. If I do this, then I can calculate, I can check del n del x is equals to half and minus del m del y is also half. So del n del x minus del m del y is equals to 1. So by Green's theorem, then that would imply that double integral over r dx dy, that is integral over c, that is the boundary, m dx plus n dy. This is a line integral. So what does this mean? It means integral from a to b, then m of xt yt, so I will write it in this form, m of xt yt, then the dot product of the curve, so m comma 0, dot product of the curve, that is x prime t comma y prime t dt, plus integral a to b 0, then n xt yt dot product x prime t y prime t dt. Now I know the precise definition of m and n. Now m xt yt, sorry, this is yt. Now m xt yt comma 0 dot x prime t y prime t is certainly m times x prime t. Okay, so I will write it in this form now. This is integral from a to b m xt yt times x prime t dt plus a to b n x t yt times y prime t dt. Okay. Now I will apply the definition of m and x, which I anyway know, that n x t yt is half xt and m x t yt is minus half yt. Okay. So I am going to apply that. So it is minus half integral a to b yt times x prime t dt plus integral a to b n xt yt is half xt, so half here, then xt times y prime t dt. Okay. So which now can be written as half integral a to b. If you want to remember what exactly the quantity is, it is xt yt, look at this determinant, x prime t y prime t dt. If you calculate the determinant, this is precisely what you get. Okay. So let us apply this formula for circle, let us say. So I take the curve ct, that is equals to a cos t, a sin t, where 0 lesser equals to t, lesser equals to 2 pi. Then the area according to the above formula is half integral 0 to 2 pi. What is xt here? Xt is a cos t. So I write a cos t, yt is a sin t, then the derivatives, that is minus a sin t, then a cosine t, calculate the determinant dt. Now calculating the determinant is very easy. It is a square cos square t plus a square sin square t, so it is just a square. So this is half integral 0 to 2 pi a square dt. So a square comes out, it is half a square times 2 pi, which is pi a square. So it matches with the formula of the area for a circle of radius r. So in general, if you have a simple closed curve C, which is given by ct equals to xt yt, then the region bounded by the curve C has an area which is given precisely by this formula. That what you do is you form the determinant xt yt, then x prime t y prime t, calculate the determinant, you get a function of t, integrate that function with respect to dt from on the range of the parameter set, that is from a to b, multiply it by half, what you get is the area. Now we will show you that there are curves which does not satisfy the criteria which we have used in the proof of Green's theorem, but for those curves the statement of Green's theorem is still true. One such example is the rectangle. So let me draw a rectangle. This is A, this is B, this is C, and this is D. This is the direction. I break it into 4 curves. This is C1, C2, C3, C4. R is the region inside. Okay. Suppose M, N, del N del X, del M del Y are continuous. So I try to calculate first the double integral over R. Let me see del M del Y first. It is analogous for the other one. dx dy. So I write down this double integral as the variation of x, which is from a to b, variation of y is from c to d. I have del m del y dx dy. Okay. So first I do the y integration. So it is a to b, then I have dx here. Now the y integral then is very easy to evaluate by again the second fundamental theorem of calculus. This is m x d minus m x c. Okay. Now these integrals I can easily calculate and see what exactly it is. If I look at a to b m x d dx, this is nothing but integral over C3 m dot dx, but with the reverse direction. So I'll put a minus sign here because the variation is from b to a now. Then minus, what remains is integral a to b m x c dx. That means I am integrating on the curve C1, okay, when y is constant, that is c. So this integral is nothing but m dx, well I should not put dot here, this integral is certainly over C1, but this is not exactly integral over Cm dx because two portions of the curve C2 and C4 are missing. So whatever is missing I write here as integral over C2 m dx plus integral over C4 m dx. But notice that on C2 there is absolutely no variation of x, and on C4 also there is absolutely no variation of x. Okay, that means these integrals are actually 0. So the end result then is minus integral over C m dx. Okay. Now if I start with n, I can do exactly the analogous analysis and I will get integral n dy. That means Green's theorem is valid even if I take the rectangular curve given by here, given by C1, C2, C3, C4. So C is equals to C1, C2, C3, C4. Okay. Similarly, if I work on some annular region, let us say this kind of, and this is my region R, then its boundary, let us say this is C2, this is C1, I give this orientation so that the region is always on my left, and here I give the other one. Here what I can do is I can actually break it into 4 regions and curves. So I will use this, so this is one orientation of the curve. So this has 4 parts where the area is always on the left, but here I will go the other way. Then this region, actually the line integrals cancel each other. Similarly, if I look at this region, then my orientation is this, then this, and if I look at this region, it is this. So you see what happens is that the line integrals on this region which I am circling, because of the reverse direction, they will cancel each other, and you get that Green's theorem is verified for this kind of regions also, which are annular regions. So let me show it by another example here. So example, so let G be the region outside the unit circle which is bounded on the left by the parabola y square equals to twice x plus 2, and on the right x equals to 2. Okay. I want to evaluate, so let me draw the curve, let me draw the region here first. So this is the unit circle, x equals to 2, and I draw this parabola. So my region is outside. Let me call this curve C1, and the inside curve I call C2. Okay. I want to evaluate integral over C1 minus y dx plus x dy divided by x square plus y square. Okay. So obviously I would choose m to be equals to, because in the Green's theorem the line integral is m dx plus n dy. So whatever is with dx I am choosing as m. So it is minus y by x square plus y square, and n equals to x by x square plus y square. And I apply Green's theorem for this region. So what do I get? I get double integral del n del x minus del m del y dx dy, that is integral over c m dx plus n dy. So C here is union of two curves, C1 and C2. I am interested only in C1. By the way, what is del n del x and del m del y? An easy calculation tells you that del m del y is actually equals to y square minus x square by x square plus y square whole square. And interestingly, this turns out to be same as del n del x. Okay? That means the left hand side integral is 0. So that would then mean that integral over C1 of the integrand, which I am not writing, plus integral over C2 of the integrand, that is equals to 0. I am interested only in the integrand C1, that then is given by minus integrand over C2. Okay. Now C2 I know is the unit circle. So I have to evaluate the line integral of the function fxy, that is equals to minus y by x square plus y square, then x by x square plus y square. So I have to do the line integral of this over the curve C2, where C2 is the unit circle. So I can take C2t actually equals to cos t sin t. Now this line integral is easy to evaluate. I look at minus, then 0 to 2 pi f of C2, that is minus sin t, then cosine t. I am not writing the denominator because cos square plus sin square is 1, dot, now C2 prime t, which is minus sin t cosine t dt. But this is minus, well, because of the reverse direction, this integral actually is not 0 to 2 pi, it is from 2 pi to 0. Because if you remember, the direction of the circle was this way. So it starts this way, goes the other way. Okay, that's why the minus sign 2 pi to 0. So it is minus of sin square t plus cos square t dt, that is equals to minus integral 2 pi to 0 dt. That means it is just equal to 2 pi. So that would mean that integral over C1 in this direction minus y dx plus x dy by x square plus y square is the integral over the C2 portion, which I have just calculated, is 2 pi. So this is all we wanted to say about Green's theorem, that you have a function whose double integral over a region is connected to an integral which has something to do with those given functions over the boundary of that region. Now we have given a proof of that result where the boundary curve satisfies certain condition except simple closed. It is there in the statement of Green's theorem that we always take boundaries which are simple closed curves, but I have assumed something additional, and under that I have given you the proof. But I have shown you one example which shows that those conditions which I am assuming on the curve C are not really needed. In fact, we can assume that if C is just a simple closed curve, then Green's theorem is true, and using that I could show that given an annular region, Green's theorem can be applied, and using that I have calculated certain line integrals which usually looks complicated, but if you use Green's theorem, then it can come down to a simpler integral. And another application of Green's theorem which I have shown is that how to get an explicit expression of the area of a region in terms of a boundary of the region. Using that, we could calculate again the area of the disk of radius r in terms of its boundary, which is a circle of radius r. So that is it for this lecture. In the next lecture, we will go to triple integrals and try to come down to surface integrals and some double integrals. So that would be generalization of Green's theorem in higher dimensions, that is in 3 dimensions.